Welcome to the deep dive. Today we're tackling, well, a really tough problem for vision language models, VLMs.
Right. We're talking about processing potentially endless video streams in real time. Think autonomous driving or maybe a helpful AI assistant that's always on.
Exactly. And the standard approach, full attention, it doesn't scale. You hit this OT complexity wall.
Yeah, it's a computational nightmare. Your memory usage just explodes or the latency goes through the roof. You either run out of memory, OM errors, or everything grinds to a halt.
And the quick fixes like basic sliding windows, they aren't great either.
Not really. If the windows overlap to keep context, you're recomputing tons of stuff, so it's still slow. If they don't overlap, the model basically gets amnesia every few seconds, loses all long-term coherence.
Okay, so that sets the stage for Streamingvlm. This framework is designed specifically for this infinite streaming scenario, trying to align how it's trained with how it actually runs.
Precisely, and it stands on three main technical ideas to get that stability and efficiency.
Let's unpack the first one. The streaming-aware KV cache. Sounds like smart memory management.
It is. The core idea is to keep the memory footprint small and stable by reusing past calculations, the key value states, instead of doing them over and over. But it's asymmetric.
Asymmetric, okay. So it's not treating all the saved data equally. What gets prioritized?
Exactly. It treats text and vision very differently. First, it holds on to a few key tokens called attention sinks. Think of them like anchors.
Anchors. To stabilize the attention.
Right. They help keep the attention mechanism stable as new information flows in. Second, it keeps a pretty long window of recent text tokens, maybe 512 or so. That's for long-term memory, understanding the conversation.
Okay, long text window, but what about the vision?
That's the asymmetry. It only keeps a short window of recent vision tokens, maybe covering the last, say, 16 seconds of video, enough to track current actions.
Hold on, only 16 seconds of video history. Isn't that risky? What if an autonomous car needs to remember something visual from a minute ago?
That's the trade-off they make. It seems, for generating coherent language output over time, the detailed text history is actually more critical than visual details from way back. Old visual data becomes less relevant quickly for the next word prediction task.
Ah, I see. So it's optimizing for coherent interaction, sacrificing some older visual detail to keep computation low.
Exactly. It retains enough context, especially textual, to stay coherent, but without the massive computational cost.
Okay, so the cache handles the data efficiency. But you mentioned we're constantly dropping old tokens. Doesn't that mess up the timing, the positional information?
That's the second major hurdle, yeah. Positional drift. When you evict tokens from the cache, the position numbers, the indices of the remaining tokens can get weird.
Weird how?
They drift apart, they're no longer consecutive. Or worse, they can grow larger than any position the model saw during training. Imagine trying to tell time if the numbers on the clock suddenly jumped into the millions. The model gets confused, unstable.
Right, it's like asking it to operate outside its known parameters.
Yeah.
So how does Streamingvlm fix this? This is where contiguous ROP comes in.
Correct. Contiguous rotary positional embeddings. It's a really neat trick.
How does it work?
When tokens get evicted, RoPE immediately shifts the positional indices of all the remaining tokens and the new incoming ones back down.
Shifts them back down.
Yeah, so they stay numerically close together, contiguous, and always within a fixed, predictable range the range was trained on. It's like resetting the positions constantly.
So it keeps the positional values in distribution, preventing that drift and instability.
Exactly. And the sources show this is key to getting stable, practically infinite streaming. They tested it on videos up to 2 hours long, and performance held steady. That's huge for real-world applications.
Okay, stable memory, stable positions. But how do you train a model for this kind of sparse, asymmetric attention pattern without needing impossibly long training sequences? That seems like the third big challenge.
Right. You can't just train it on infinite video. The cost would be astronomical, back to that OT problem. So they needed a training strategy that mimics the inference conditions.
And their solution is this overlap chunk, full attention training.
That's the one. They take long videos, but chop them into short chunks, say 24 seconds long. Crucially, these chunks overlap significantly, maybe by 12 seconds.
So consecutive chunks share a lot of frames.
Yes. And within each short 24-second chunk, they do use standard full attention.
Okay, why the overlap? How does that help?
The overlap is the clever part. It forces the model during training to constantly deal with context that was present just a moment ago, but might be partially or fully gone in the current chunk's view. It learns to reconstruct or work with that partial context.
Ah, so training on these overlapping full attention chunks naturally teaches the model the kind of recency bias and context juggling it needs for the actual streaming inference with its sliding window and attention sinks.
Precisely. It aligns the training objective with the inference reality, without ever needing to run full attention over hours of video during training.
So bringing it all together, this asymmetric KD cache for efficiency, contiguous rope E for positional stability, and this overlapped chunk training strategy for alignment.
That's the trifecta. And the results are pretty impressive. Stable performance, low latency, staying under that real-time threshold. They report up to 8 frames per second commentary on a single H100 GPU.
Which really brings us to the final thought. If you have VLMs that can process and reason coherently over, say, 2 hours of continuous video without forgetting crucial context, what does that enable?
It opens the door to truly persistent AI agents, doesn't it? Systems that maintain situational awareness over much longer timescales.
Yeah.
Think about robotics, long-term monitoring, assistants that actually remember your entire day. What new applications become possible when forgetting isn't the default state every few minutes? That's the frontier this kind of work pushes towards.